This video is going to cover the conjugate beam method. It's personally my favorite method of all of the slope and deflection methods. I like it because we take the moment diagram that we find using superposition and we load it onto our beam. So we first unload our beam, we load it with the moment diagram, and we have to change the current reactions that we have here. For instance, a pin and a roller, we have to change those into a conjugate beam. So if our, and can't forget about our free end as well, if our current beam were to allow for rotation, we're going to have a shear reaction that's a slope. So a theta. And if it allows for translation, aka deflection, it's going to have a moment that is deflection. So our del that we use for deflection. So first things first, we're going to find slope at B. Kind of helpful to know what is B. We have A as our pin, we have B as our roller, and we have C at the end. And we want to find the slope at B, where we're going to take counterclockwise to be positive. And we're going to find deflection at C, where upwards is positive. So again, we have to first find our moment diagram. So we need to pick a side that we're going to fix it at. And for this example, we're going to fix at A. So what we do need to find is BY. So what we're going to do is we're going to start by summing the moments about A and setting it equal to 0. I always like to take counterclockwise to be positive. So I'm going to work left to right. So we're going to start with our 6 kip force, and he's going to be creating a negative moment. And his distance is 6.2 feet. Then we are going to have BY, and BY is going to create a positive moment. He's going in our correct direction, and he's going to be times 6.2 plus 6.2, which is 12.4 feet. Then we have the 12 kips going in the wrong direction, so minus 12 times 6.2 times 3 is 18.6 feet. So we can find BY, and BY is going to be 21 kips. He is positive, so he's going to be going up. Great. So next thing we need to do is find our moment diagram using superposition. And again, we're going to fix over here at A. Probably need to make that just a little bit longer. Okay, so we're going to fix over here at A. We're going to have the 6 kips going down. So again, we're going to start at the spot where the point load begins, and it's going to go down. So it says down, so we're going to be going in the downward direction, P times L, because that is a moment for a point load. So down P times L, so P is 6, L is 6.2, so that's going to give us 37.2 for our moment diagram. Then we have BY. BY is going up, so we're going to start BY. And since he's going up, our triangle is going to be going in the upward direction. So again, P times L going in the upward direction. P times L, P being 21, L being 12.4. This is going to be 260.4. Lastly, we have the point load at C, who is 12 kips. So he's going down. So he's going to start at that spot, and he's going to go down to P, which is 12 times L, which is 18.6. He's going to go all the way down to 223.2. So 223.2. Cool, so there is our moment diagram. This is what we're going to use to load our beam. So, next thing, we need to create our conjugate beam. So our conjugate beam, it just looks better when you use the ruler. Okay, our conjugate beam. At A, we allow for rotation. So since we allow rotation, we're going to have a reaction, a shear reaction, that is a slope. Now, remember that this is kind of like a graphical method going from our loading diagram to our shear diagram to our moment diagram. That's this guy over here, our moment diagram. Then slope is the area under the curve of the moment diagram. So now we're going to treat our moment diagram over here like it's our load, and we're going to do the same thing again. So we're going to take from our load, we're going to go to our shear, which that's going to be our slope here. And from our shear, we go to our moment, and moment is deflection. So that's why those reactions are what they are. So that's for A. Over at B, B's going to get a little weird. Because B is a midspan roller, he's actually going to become a hinge. So he's a hinge. Kind of awkward, but that's what he is. And then don't forget your free end at C. So at C, we definitely allow rotation. So we're going to have a slope at C, but he also allows for deflection, right? He allows for that translation. So we're also going to have a moment deflection at C. So the really cool thing is, if we want to find slopes, you're literally solving for your vertical reactions. And if you want to find deflections, you're solving for your moments. So now we just need to load this beam with the forces that we have on our moment diagram. So currently we have the red one, and I'm going to draw in these cute little arrows here just to show you that this is going to be going up. Okay, so we're going to draw our little triangle. Oop, I got so carried away there. We draw our triangle, and because it's a negative moment, instead of normal loading is positive, and normal loading is like going down. So this guy's negative, so he's going to be going up. So we load him. We just flipped him upside down, but he's still going up. Then we have the blue one, and the blue one is going to be going all the way to B. So over to our hinge here. And he is positive, so he's going to be going our normal direction, which is down. Then we have our green one, and our green one goes all the way over to C. So he's going to be quite big. So I might need to scoot all of this guy down some. Oh, that is just the ugliest line I've ever drawn in my life. Okay, close enough. Okay, so again, this guy is down, so he's going to be going in our opposite from our normal direction, right? Upward. So that's our diagram with our loads. Very fun, very fun. Now let's label them. Remember, our green one is 223.2. Our blue one we said was 260.4. And our red one we said was 37.2. So now we just need to solve this as if this was our really awkward beam. And we've got our reaction forces. So we said we want to find slope at B. So if we want to find slope at B, maybe we should break our free body diagram at our hinge. So I'm going to do just that. I'm actually going to erase what's coming off this way real quick. And we're on the inside here using some solids. We've got a vertical force at a hinge, right? And that vertical force is our slope at B. Now technically also at a hinge, you have a horizontal, but that doesn't really make any sense here. We're not doing any normals, no axial forces, so we're going to just disregard his existence. So what we can do if we want to find the slope at B, remember that this cut goes all the way up, and we're going to disregard this right half over here. We're going to kind of pretend he doesn't exist for a second. So what is this distance? If this was 6.2 feet, and this was 12.4 feet, then we need to find the height right here. Because when we start taking our moment, we're going to have a triangle and a little uniformly distributed load as a rectangle acting in here as well. So if I want to find that, that's going to be with similar triangles. We have 6.2 over whatever that y height's going to be is equal to 12.4 over 223.2. Rearrange it and you're going to get that height is equal to 74.4. So cool. We have 74.4. So now, again, if I want to find the slope at B, I should probably sum the moments about A, and that'll get rid of our slope at A. So we're going to sum moments about A, going counterclockwise is positive, set it equal to 0. And we're going to do it for all of these wonderful triangles. So we'll start with the red one. We'll go from bottom to top. So we have 1/2 the base, which is 6.2, times the height, 37.2. He is going to be creating a positive moment, so that's good. Then his distance is 1/3 of the base, which was 6.2. Now for the blue one's going this way, that's negative. So we have negative 1/2 times the base. The base for him is going to be 12.4 times the height of 260.4 times his distance of 1/3 times 12.4. Then we have the little blue rectangle here, and he's going up, so he's going to create positive. I guess I'll just scooch over and add him in here. So positive, he is the base times the height, and the base is 12.4, and the height we said was 74.4. Then we have the green triangle. The green triangle is also going up, so he's going to create positive. So plus, we have 1/2 the base of 12.4, the height, who is actually 223.2 minus the 74.4 dude, right? Because we're actually only taking the triangle part of things, times the distance from him, which is 1/3 of his base, which is 12.4. All of that. Super delicious. Plus, don't forget we've got slope at B over here going positive. So we have plus slope of B times his distance, 12.4. So sorry that it got all out of hand there in terms of our equation, but there it is all written out. So when you solve for that horrible monstrosity, you're going to get the slope of B is equal to negative 250 kip feet squared over EI. So honestly, pretty simple. Honestly, pretty simple. So if we want to go through and now find the deflection at A, I kind of need to go bring back the rest of that diagram. So for deflection at A, we had a slope at A and a deflection at C. These are C. We're finding deflection at C. So we can go back to our partial free body diagram. We could find slope at A, and then you could sum the moments about C and do that, or we can take our cut that we had before and we can ignore this side. And that's a really easy thing to do, right? That makes that really simple. So we'll just erase him. And now we don't need any of these loads. Kind of need that guy just a little bit, just to mark where he's at. But theta B was going up over here, so actually he's going to be going down on the other side. Remember, because he's a hinge, he's equal and opposite in direction. So he's equal and opposite at a hinge. So now, that's a much simpler thing to solve for. So just to complete getting rid of everything else, remember that the height we found over here was 74.4. And that is a much simpler thing. So what we can do now, and this is 6.2 feet, now we can sum the moments about C and set it equal to 0. We're going to take counterclockwise to be positive. We already have theta B, so let's go ahead and use him, right? So he's going to create a positive rotation, right? He's going that way around. So he'll be a positive rotation. So we have theta b times his distance of 6.2 feet. And then we have deflection at c. He's going the wrong way. So minus deflection at c. Then we have this glorious thing creating a moment again the wrong way. So we have minus 1/2 the base of 6.2 feet times the height. The height we said was 74.4 times the distance from his centroid, which is over here. So that's going to be 2/3 times the base of 6.2. So we're going to get, for deflection at C, we're going to get negative 2,500 kip feet cubed over EI. So honestly, much simpler of a problem. Now you might think it's pretty simple, but the most difficult thing was the hinge. That's honestly as hard as it gets for conjugate beam.